video and also share my screen. Yes. Okay.
Yep, I can see it. It's great.
Yeah.
Okay, great. Go for it.
Okay, perfect. Yeah, so thanks a lot for inviting me again to this kind of mini symposium. I will actually speak about something quite different to last time because I thought it might be interesting to also show you these ideas from our random dynamical systems community on questions around oscillators, stochastic limit cycles, and so on. So I will talk about shear-induced chaos and some difficulties, but also resolutions, how to prove this phenomenon in stochastic Hopf systems. So this has been worked together with Jeroen Lamb and Martin Rasmussen from Imperial College and Tai-Son Nguyen from Vietnam University. So Hanoi University in Vietnam, sorry, there's not just one university in Vietnam. And Maxime Engel, who was actually my office colleague in TU Munich and is now at École Polytechnique. And we did some computer-assisted proof stuff together, which I find quite exciting and I will come to at the end. So I will talk a little bit about this idea of bifurcations in random dynamical systems, in particular for this problem of Hopf bifurcation, and introduce some ideas we developed in the last years, how to get a new view on these random dynamical systems bifurcations, namely by something we call quasi-ergodic random dynamics. And in the end, I will show you how to apply some of the theory to the stochastic Hopf bifurcation in terms of this computer-assisted proof. So yeah, just let me start with our background. So we wanted to understand at the beginning of this kind of research more about bifurcations in stochastic differential equations. So if you assume that you have some bifurcation parameter in your drift in a stochastic differential equation and you forget about the noise for the moment, then you might observe some interesting bifurcations, in particular in two-dimensional systems. This can become, of course, more and more interesting, and then want to understand what does the noise add to this picture. Does it in some way change the bifurcation? Does it preserve it in some way? So one question was, is the bifurcation still present in the stochastic case? And if yes, in what sense? And the other then was if there's a new bifurcation scenario possibly, which can come up with interaction of other parameters, which were already there in the deterministic system hidden here, but didn't really have any impact on the qualitative behavior, but only with an interaction with noise really make an impact. So there are two objects that are important for the following. So the one, as already mentioned in talks before, is a stationary ergodic density for such an SDE system, which is a stationary solution of the Fokker-Planck equation, which is the formula L2 adjoint of the generator. So these are two differential operators, second order differential operators, L and L star. And usually this kind of stationary ergodic density gives you some average behavior of typical trajectories, or it's the density that really shows you how trajectories in time average will distribute over space. And so this is more like a statistical point of view, which we want to use then for our point of view, which is really more this random dynamical systems point of view, where we try to understand solutions of SDEs as trajectories for fixed omega. Also we fix, similarly maybe to Sarah's talk, where she compared oscillators for fixed noise samples. We fix a certain noise sample and then understand the solutions of the SDE as exactly these solutions for these fixed noise samples with different initial conditions and compare these trajectories. And we write it in this flow kind of way, where you have to take into account that the noise is a non-autonomous driving, so you always have to do some time shifting in your noise space. Otherwise, this is kind of a flow property, and for well-behaved SDEs with unique solutions, you can usually find these random dynamical system solutions. And this point of view is something we then started to apply to this Hopf problem of additive noise. So this is just an easy normal form for a Hopf bifurcation in alpha with some just additive noise. And included is something which can also be called shear, and especially Lyson Young also always called it a shear force, but it comes up in different contexts. because it is an amplitude phase coupling. So it couples in polar coordinates phase and amplitude of the problem. And because you have convergence either to an equilibrium or limit cycle in the original Hopf system, this shear, which really makes a difference for the angular velocity in terms of the radial component, doesn't really come up. But of course, when you're kicked out with some noise, this might really make a difference. So first of all, if we really only look at the not so complicated picture, so in a non-noisy system, of course, you only have this typical Hopf bifurcation from alpha smaller zero having an attracting equilibrium at the origin to alpha bigger zero having an attracting limit cycle. And then if you only look at this stationary density, then this really mirrors this bifurcation in a way. You see that, okay, this is something which you can easily compute actually explicitly from your Fokker-Planck equation for this particular problem. And then you see there's no dependence on this shear parameter B, but it really only depends actually on this alpha and on the noise, of course, noise intensity, and this A just locates basically the limit cycle or gives some additional stability parameter. But generally, so you mirror this kind of bifurcation and nothing really interesting in that sense happens. So to answer this one question, the bifurcation is preserved, but dynamically, we are more interested in what happens to something like an attractor. So we look for these fixed omega, as I announced. We look now at something we call a random attractor, which is a pullback object in the sense that we want to fix some omega and then we want to go back in time on our omega space and go forward in time exactly this amount. And I think in this other talk on this, this idea of capturing random isochrons in a random dynamical systems way, I already came up with this random attractor these 2 months ago, and it's the same concept here. The interesting thing now is that we have two kind of behaviors with this additive noise. So we can have, when we start with this point cloud here of initial points and apply exactly the same noise and do this random pullback attraction, then we actually for small b, small shear, and any kind of alpha around zero, positive or negative, we see synchronization. So we really see synchronization to a point. If we would now go forward in time from this point, this would be just a trajectory, but this is the pullback picture. So we really can fix a point here as a random attractor. If now the shear is very large, you see that it kind of gets the character of a new bifurcation parameter. The alpha doesn't really matter anymore, but the shear really brings you from this contraction to one point to a chaotic random attractor. So something which has a fractal-like structure. And the question is now, how do we prove this? How do we measure that? And the typical way to measure in what kind of situation we are is by looking at the Lyapunov exponents, in particular the leading Lyapunov exponent. So these Lyapunov exponents are these exponents or rates of expansion and contraction along the linearization of our system on the tangent space. And the sum of these Lyapunov exponents in these examples will always be negative because we have contraction of all the mass, so there's volume contraction. But then in this one case of the chaotic attractor, there's some divergent direction. So this indicates there must be some positive Lyapunov exponent here. And it's quite hard to show that. So what we could show quite easily was the synchronization case straight away. So if the shear is small, then we have that there's a negative top Lyapunov exponent, and the random attractor is actually something we call random equilibrium, and we have synchronization of almost all trajectories. So also similarly to Sarah's talk where she mentioned potentially uniform contraction rate given by a negative Lyapunov exponent. This is not hard to show, but it's much harder to show the positive Lyapunov exponent due to the following. So this Lyapunov exponent can be expressed by a formula, by an ergodic formula, for having a functional actually in terms of the Jacobian of our vector field in the SDE. If there would be not additive noise but more complicated noise, then you would also have some diffusions terms here, but in this talk, we only focus on the additive noise case. So we really get this functional depending on the Jacobian and then on the directions, the angular directions actually on your tangent space. So this gives a kind of rate for the growth of your norm of the linearization. And this growth is something we want to measure actually in time averages, and due to ergodicity, we can also measure it in this closed formula with this integral. If this, if there's a certain invariant or even ergodic measure rho on the joint space of the original problem space or the original state space, which would be R2 here, and actually the tangent space, or at least the tangent angular direction as one. So this is actually a tangent bundle problem, and if there is a unique stationary distribution, ergodic distribution here, which solves the according Fokker-Planck equation, then we can express this Lyapunov exponent like that. The point is now that for this functional here, which is negative, then we can easily show level 1 being smaller than 0. But in the case with the positive Lyapunov exponent, they will be contracting and expanding direction. And then it's very hard to show what wins. You need to have a lot of information about this. What we would do was to see Dyson Young and co-workers who did a lot of very nice work on this problem, especially for periodically kicked oscillators. And they also did some numerics with Kevin Lin on this, continuously stochastically perturbed problem. And here you see, so we only in the R direction and the amplitude direction, we now only have some linear contraction. We took the shear here also in a linear way, and then we want to play around a little bit with the noise in order to see what can we do in terms of proving something. And actually in this reduced linear easy model, if you have a certain orthogonality condition for these diffusion terms here, then for this shear-induced problem, you can actually show a positive Lyapunov exponent for large shear and show that A is a chaotic attractor. So you can make explicit computations of these Lyapunov exponents, and that shows the conjecture for that kind of limited problem. So here is again some pullback random attractor now on cylindrical coordinates, which just illustrates numerically what we can prove in terms of the Lyapunov exponent. So, but still, we don't have a positive lambda 1 for the full model with the large shear, which I showed you at the beginning with these additional nonlinearities. And in particular, there might even be more nonlinearities. There might be even more higher order terms. I'm only talking about normal forms here, but of course I might want to look at this for just a whole class of stochastic Hopf bifurcations. And to get this a little bit under control, we developed a new idea, which we called random or quasi-ergodic dynamics, which is based on the observation that the stability and bifurcation phenomena, especially in the deterministic case, they are all local, they happen around equilibria, and then limit cycles arise, and this happens, in these cases I showed you as local bifurcations, but the noise makes everything global. Especially if you have additive noise, you really just explore the whole state space, and this doesn't really fit, so this can kind of smear certain pictures and make it a little bit unclear. So what we suggested was to now concentrate on bounded domains and just say we look at the process which solves the SDE and then the induced random dynamical system only on a bounded domain which fits our problem up to a certain stopping time where the process hits the boundary. And then when it hits the boundary, forget about it. So the setting of killed processes. We can accordingly look at the random dynamical systems only for trajectories that survive in here. The point is now that there's not really stationarity, there's only something called quasi-stationarity, and there's also not really ergodicity, but something called quasi-ergodicity, which means that if you look at your time averages and your typical Birkhoff's ergodic theorem, then what you need to look at is actually some conditioned expectation on survival. So this always means that we are only looking up to times which are smaller than the hitting time of the boundary, and up to their condition on all the trajectories that have survived. And this kind of renormalization take the expectation of these conditioned expectation of these quantities, and then in the limit this will actually converge to an integral with respect to a quasi-ergodic distribution for observables. So this is like a Birkhoff-Ergodic theorem, but just in a conditioned way. And this is exactly what we need and want to use for looking at Lyapunov exponents. So if we look at the finite time Lyapunov exponents, so really these measures of expansion and contraction up to a certain time, now up to a certain time which is smaller than the survival time for fixed omega and x problems, then we want to see how they converge. And if we can assume that there is a joint quasi-ergodic distribution for this unit tangent bundle process, which comes up in this ergodic Furstenberg-Kosminski formula for the Lyapunov exponent, then we can actually show that there is convergence to something we call conditioned Lyapunov exponent of these finite time Lyapunov exponent in this conditioned way upon survival. And this conditioned Lyapunov exponent satisfies again something like a Furstenberg-Kosminski formula, now with respect to this quasi-ergodic distribution on the tangent bundle process. What I want to mention is that we can also prove that these finite time Lyapunov exponents really converge in the strongest way possible in this kind of setting to our conditioned Lyapunov exponent. So in LP for P bigger equal 1 and smaller equal 2, and by that also in the conditioned probability, we can show some stable manifold theorem that the negative Lyapunov exponent really means that there's local synchronization of trajectories, and we see this positive Lyapunov exponent again as a measure of chaos. And what is also important, that this QED in nice elliptic cases, so this quasi-ergodic distribution, can be expressed via eigenfunction of our Kolmogorov operators. And this is something we make use of course, in this computer-assisted proof. So if we now turn back to our Hopf system from the beginning, and then we can actually look at the unit tangent bundle process, in this case, quite luckily, in a two-dimensional way. So that's actually 3 dimensions, right? We are in a state space for the nonlinear system in 2 dimensions. So this was on the plane, and then we need to take into account also the angular direction on the tangent space. But via a trick by De Ville and Namachivaya, who looked also at this problem some years ago, you can actually reduce this whole thing in the Hopf case to a 2-dimensional problem. So this is still the radial direction from the nonlinear problem, but this is a mix. This is like a combination. This psi is a combination of the nonlinear and the linear angle. So you can reduce this to a 2-dimensional problem and look at the Furstenberg-Kosminski functional. So this functional that came up in our Lyapunov exponents formulas, and really get a nice closed formula. So the point is that the original Lyapunov exponent, again, on the whole space would be now given by this formula for P being a density which solves the stationary Fokker-Planck equation, now in these transformed coordinates. So we have a 2-dimensional problem, and you could maybe hope to get something there, and then maybe make a statement about this largest Lyapunov exponent. So I found it extremely difficult, and I didn't really see anybody really making a rigorous proof that for certain parameter values of this B, this can be positive. So this is something that at a certain point actually seemed out of reach. So that's why we also looked at the cylinder model, and there we could prove something. But this whole problem, really making a good approximation of this distribution P in a completely rigorous way, seemed very hard. But we had this idea with the quasi-ergodic dynamics, and now we could actually transform the problem to that. So look at the conditioned Lyapunov exponent now on an annulus. So we also take the origin out, and we go up to a certain radius. And then on this, we can really try to compute this conditioned Lyapunov exponent, which has this Furstenberg-Kosminski formula with respect to a quasi-ergodic measure, which again is a product of these eigenfunctions eta and phi, for the largest eigenvalue lambda 0 of our Kolmogorov operators. So this eta is actually the according eigenfunction with our generator with the Dirichlet boundary conditions on the boundary of our domain, and it roughly looks like that after computation. And the phi is the according eigenfunction for the Fokker-Planck operator. It's actually the quasi-stationary density for the people who are interested, but there's a little bit of a difference to the quasi-ergodic one here. So we can compute these numerically, and now we have to prove that they are actually close enough to our right ones. And this is exactly what the computer-assisted proof is about. So if we look at this Hopf process on an annulus, as I said, then we can now prove a certain parameter set. So we have shown, we have calculated through certain parameter sets for our alphas and our sigmas, and then can see that on certain annuli, there are certain shear forces for which we can actually prove rigorously that the conditioned Lyapunov exponent is positive by a computer-assisted proof. And just a short way of summarizing this computer-assisted proof, which was actually yesterday talked about by Maxime Bredin and me, but especially then about the computer-assisted proof by Maxime Bredin at a seminar organized by people from Montreal on computer-assisted proof. So this should also be online if you're interested. So the you can compute these numerical approximations of the eigenfunctions, and then you have to show that our actual eigenfunctions are contained in some small neighborhoods of these numerical approximations. And then you use some Newton-Kantorowicz type theorem, you define a proper operator, show that it is a contraction, and you need to rigorously show that it is a contraction, and this involves all the Fokker-Planck, like the Kolmogorov operators, and then reducing these to some easier operators and using some homotopy methods to get to the actual operators. And it's really a very involved proof, and I think Maxime Bredin really did great work there. He was mainly responsible for putting this through and then validating the whole thing with interval arithmetic in MATLAB. So this was how we solved this problem in the end. So to give you a short summary, this problem of proving positive Lyapunov exponents is highly challenging. I think as people in ergodic theory know, and we wanted to prove it for this Hopf bifurcation with shear noise. We were able to do it in a reduced model. We wanted to do it for the full problem and actually found this idea of the conditioned Lyapunov exponent generally as a new relevant concept for stochastic bifurcation theory, and then we're able to apply this kind of setting to a computer-assisted proof. Just recently we got the full computation, and this paper is in preparation. The other three, which I talked about, led to this paper and can also be looked up if you're more interested. So thank you very much for your attention.
Thanks a lot, Maximilian. Any questions? I have a quick question. Oh, so you go, Peter.
Mm-hmm. I just have a possibly a very silly question. I'm just wondering, what's the standard way that people define bifurcations in the stochastic context?
So there's the way that you can differentiate between two kinds of bifurcations, and that's what I didn't mention that precisely at the beginning, but that's kind of what it showed here on the picture. So there's something that people would call p-bifurcation or phenomenological bifurcation, where you have a bifurcation really of the stationary density, which kind of mirrors this bifurcation in a deterministic way. But then if you look at the random dynamical system, then there are also some different views, but mainly it's really that the stability of some invariant measure changes. And in our case, it would be that you have some delta measure here, which is associated to the random attractor, and this is a point measure, so a delta measure. And then this in some way bifurcates into something where you now have something like an SRB-like measure on a random attractor. So this would be a kind of different dynamical point of view of this bifurcation. I think a quite easy point of view there is also just a change of the Lyapunov exponent from the first Lyapunov exponent from negative up to positive.
So in the first case, the p bifurcations, I guess you would say there's a bifurcation if the densities changes its like, let's say, you could define a notion of topological equivalence, like in singularity theory, and you could say that its topological equivalence class changes or something like that. Like, and the one on the left.
So I mean, roughly you would say the shape changes, I mean, in a sense, this change of topological. So no topological equivalence anymore. This is also something where you can look into. So this would definitely be the case here, right? I mean, here you definitely can't have any topological equivalence anymore in this dynamical setting. In the phenomenological setting, just in terms of the densities, it's maybe hard to talk about topological equivalence, right? Because you don't really have topological dynamics here. It's really just the shape of the density. You can
Well,
describe this also topologically, of course, yeah, in that
well,
sense.
what I mean, like Christopher Zeeman in 1988, he had this paper where he proposed to, instead of structural stability for deterministic dynamical systems, he proposed to take a deterministic dynamical system, add small epsilon diffusion, look at the density. And so, you know, he was a guy who was big in singularity or catastrophe theory, and they defined notions of topological equivalence for functions. And he proposed to disambiguate deterministic dynamical systems just based on the topological equivalence class of their stationary densities once you add epsilon diffusion. And it just strikes me that you could do the same thing here, I think, but I don't know if people do that. But it's topological equivalence in like the catastrophe theory or singularity theory sense.
Yeah, fair enough. No, this is, I can see this point. Yeah, I mean, this makes a lot of sense. This adding small diffusion to see some shapes or learning something about the system. I know that in the Gaussian coherent structure community, this has also recently been applied in some sense. Yeah, I guess you can relate it to these topological questions. Sure, I mean, you can say that this density now has a different, just as a surface, for example, just as this different shape here as you see, and can measure that topologically. But I'm not really, I haven't really focused so much on these questions, right? As you can see then later on that my work is more focused on these questions of random dynamics, and to show these changes in the Lyapunov exponent and the random attractor.
Okay, thanks a lot, Max. That was great, really interesting. I think we've got time, so I have a quick question about, I don't know if you've got intuition, when you talk about chaos, my intuition, what does that mean? So you have the same noise, you have two different starting positions. What would you expect to happen? I
would expect to happen that the point is there's basically at least no synchronization, right? There's something, so you have these two different starting conditions here, and then you have conversions to this attractor, but not really, like these two different starting conditions and trajectories don't really converge to the same point there, or to the same trajectory. But there's really on the attractor then going on something which is not just, trivial synchronization, but really gives some new dimension to the whole random attractor. And this is something, loosely I would be happy with to call chaotic attractor here.
Okay.
And then you can measure that also in terms of the random measure on that. Yeah.
I see.
So just to Peter here, if I chose a noise sample and then I move forwards in time along it, I would see the shape on the bottom right would be sort of moving around continuously in time, right? If this is just like a snapshot. So this the random chaotic attractor would be, it's not a static object. It's sort of
as a pullback object, it is static. That's the trick of the pullback.
But if I took a different noise sample, I would get a different one. And if I took a family of noise samples that were sort of related by this shifting operation, then would they be would I be continuously deforming?
Yeah, if you go forward in time, I mean, if you don't take minus t here, but if you just take an omega here, and you take the t here so you take phi of t omega x, and then you have to take care of the shift in the forward direction. So you would always then come closer to the a of theta t omega. So you would really shift in your noise space with the attractor, as your intuition just was completely right. Yeah. So you would then go forward in time along this attractor.
But in a continuous way. So
yeah.
Okay.
Okay, I think that's probably time, but thanks again, Maximilian. That was really great, and everyone else as well. It's been a great mini symposium.